4 millennia, humanity has chased a ghost: perfect, unwavering time. From sundials to mechanical clocks, we've built machines to capture its fleeting essence. In the 20th century, we thought we had finally done it. We built the ultimate timekeeper, a clock so precise it would lose only 1 second every 100 million years. We harnessed the very heart of the universe, the atom. But in our quest for perfection, we overlooked a fundamental truth. Our planet, the Earth itself, is not perfect. And this cosmic discrepancy would lead us to the brink of a global technological crisis, not once, but twice. This is the story of the second that almost broke the world. To understand the crisis, we first need to understand the clock. An atomic clock isn't like the one on your wall. It doesn't have gears or a pendulum. Instead, it measures time by listening to the universe's most reliable rhythm, the vibration of an atom. Specifically, the cesium-133 atom. Inside an atomic clock, cesium atoms are stimulated by microwave radiation. When the microwave frequency is just right, the atoms resonate and change their energy state. This resonance happens exactly 9,192,631,770 times per second. It's an unchanging, fundamental constant of nature. By counting these impossibly fast vibrations, we define the second with incredible precision. This is Coordinated Universal Time, or UTC, the world's official time. By the late 1960s, a global network of these atomic clocks provided a single, unified heartbeat for our increasingly connected world. From financial markets to telecommunications, everything was synchronized to this perfect, atomic pulse. We believed we had tamed time itself, but we forgot we were living on a spinning, wobbling ball of rock that plays by its own rules. The Earth's rotation isn't constant. It's slowing down, very gradually, due to the gravitational pull of the Moon. This means that a day, as measured by the sun rising and setting, is getting slightly longer. While atomic time marched on with perfect, unyielding precision, solar time was falling behind. By the early 1970s, the gap had grown. It was only a few seconds, but in a world run by atomic clocks, a few seconds was an eternity. This brings us to 1972, the year of the first great desynchronization. The world's timekeepers were faced with a terrifying dilemma. The official time, UTC, was now nearly 10 seconds ahead of the Earth's actual rotation. If they did nothing, noon would eventually happen in the middle of the night. But how do you fix it? You can't just slow down every atomic clock on the planet. Their very purpose is to be unchanging. The problem was debated fiercely in scientific circles. Some argued to let the two times drift apart, creating separate atomic and solar timescales. But this would create chaos for astronomers, navigators, and anyone who relied on the position of the sun and stars. A more radical solution was needed. A kludge, a patch, a fudge factor for time itself. They called it the leap second. The plan was simple, and in its simplicity, terrifying. On June 30th, 1972, at the very last moment of the day, the world would add an extra second. The official time would read 23 hours 59 minutes and 59 seconds, then 23 hours 59 minutes and 60 seconds, and only then tick over to midnight. This would allow the lagging Earth to catch up, realigning atomic time with solar time. It was an elegant solution on paper, but its implementation was a step into the unknown. In 1972, the digital world was in its infancy. For most people, the addition of a leap second went completely unnoticed. But for the engineers managing the world's nascent computer networks, it was a moment of high tension. They had to manually adjust their systems, hoping the unprecedented 61-second minute wouldn't cause unforeseen bugs. It was a global, synchronized patch on the very fabric of time. The operation was a success. The world didn't end. And so, the leap second became a regular, if infrequent, feature of our lives. Every few years, when the discrepancy between UTC and Earth's rotation neared 1 second, the International Earth Rotation and Reference System Service would announce another leap second. For decades, this solution worked. We got used to the occasional temporal hiccup. We updated our systems, wrote new code, and built protocols to handle the jump. But as our reliance on technology grew, so did the potential for disaster. The intricate web of satellites, financial systems, and power grids was all built on the assumption of a smooth, continuous flow of time. A 1 second jump was a 1 second anomaly, a moment of pure chaos in a world that demanded order. And in 2019, we saw just how fragile that order was. On January 26, 2019, something went wrong with the Global Positioning System, GPS. The system, a constellation of 31 satellites each carrying multiple atomic clocks, is the invisible backbone of modern civilization. It doesn't just tell you where you are, it provides the precise timing signals that synchronize everything from cell phone networks to banking transactions and electrical power grids. That day, a software update, a routine part of a system-wide clock correction, went awry. The error, known as a CNAV upload anomaly, introduced a tiny 13 microsecond timing error into the GPS signal. 13 microseconds. 13 millionths of a second. It sounds like nothing, but to the global network of systems that rely on GPS for their heartbeat, it was a catastrophic shock. Reports began flooding in from engineers around the world. Scientific instruments, seismic sensors, and radio telescopes suddenly lost synchronization. Their data became corrupted, useless. The FAA in the United States reported anomalies in their ground-based navigation systems, forcing them to issue warnings to pilots. The problem was global. The invisible pulse that runs our world had faltered. Engineers at the Air Force Base responsible for GPS scrambled. 4 hours, they worked to diagnose and roll back the faulty update. It was a race against time, a race to fix time itself. The 13 microsecond glitch revealed a terrifying vulnerability. Our civilization had become so dependent on perfect, atomic time that even the slightest deviation could cause widespread failure. What's more, this was a glitch of just microseconds. What would happen during a full 1 second leap second? The crises of 1972 and 2019 taught us a profound lesson. Our attempt to create a perfect, man-made time has put us in conflict with the natural, imperfect time of our own planet. The leap second, once a clever solution, has become a ticking time bomb at the heart of our digital infrastructure. Every time we add one, we risk another, potentially larger, GPS-style glitch. The debate is now more heated than ever. In 2022, at the General Conference on Weights and Measures, the world's leading metrologists voted to abolish the leap second by 2035. They argue that the risk to our critical infrastructure is too great. We should let atomic time run free, even if it means our clocks slowly drift out of sync with the sun. Others argue this is a mistake, that tying our time to the sun and earth is a fundamental part of what it means to be human. The final decision has yet to be made. We stand at a temporal crossroads. Do we embrace the perfection of the atom, or do we remain tethered to the familiar rhythm of our spinning world? The story of the atomic clock is a modern fable. It's a story about humanity's ambition, our ingenuity, and the unintended consequences of our creations. We reached for the stars, for a perfect and eternal measure of time, only to find ourselves in a battle against the very ground beneath our feet. The silent, invisible war over the nature of time continues. The next time you check your phone, remember the incredible, fragile system that makes it possible, and the leap seconds that hold it all together for now. Thanks for watching. If you found this journey through time interesting, be sure to like and subscribe for more stories from the edge of science.